Hello everybody, hope you're doing well and thanks for joining us for another video where today we're going to be debunking some more flat earth memes and Twitter posts. I did a video looking at some a while ago, but there were just too many to cover in a single video. So let's address some more that either completely misunderstand physics, outright lie, or in some cases prove the earth is a globe. For example, we have this one, which says Peak Canigou seen from Marseille 163 miles away. At this distance, the mountain should be hidden behind 2.5 miles of curvature. Now, if a flat earther presents you with this, you can debunk it in one of two ways. You could debunk it by taking the latitude and longitude coordinates off the picture for the observer's location, see that they were standing near this chateau, using elevation finder to see that the observer's height is almost 300 meters above sea level, going to an earth curve calculator, plugging in those figures, and getting 1.9 miles of obstruction, not 2.5. You get 2.5 if you put the observer's height at 300 feet, not 300 meters, but anyway, that's still almost 2 miles of mountain obstructed. But then you remember that the Earth curve calculator is only working on basic geometry and not accounting for the fact that there's an atmosphere which refracts light. So you instead go to Walter Bislin's advanced Earth curve calculator and plug the same numbers in, but then include standard atmospheric refraction, and you realise that on the non-strawmanned version of the globe, there would actually be about 288 meters of the mountain visible. However, I think the more effective way to debunk this is instead, given that there are multiple mountain peaks which are quite distinguishable, instead go to Google and image search for Canigou Mountain, grab a photo like this, overlay it onto the sunset photo, scale and reposition it so that the peaks all align with each other, and then ask the flat earther how is more than 3/4 of the mountain below the horizon. Because the reality is that this photo, like pretty much all long-distance photos that flat earthers like to bring forward as evidence, actually go and prove the earth is a globe. Often it's brought up by flat earthers as evidence because it either doesn't include atmospheric refraction and or they haven't got an accurate observer height. Much the same as this one, Chicago skyline from Michigan, 50 miles across level water, 1,667 feet missing. Now, even just a basic Earth curve calculator with this, you find that you can only get 1,667 feet of obstruction if you have the observer height at literally 0. And it should be pretty clear from the photo that the camera is definitely higher above the water than 0. Now, there's no information in the meme about exactly where this photo was taken from. However, we can see that the tallest building in the shot is the Willis Tower, and to the left of that is one Chicago Tower. Again, seems the vast majority of Chicago is below the horizon. However, one Chicago Tower is only just showing above the horizon, and yet that building is 295 meters tall. Now, if we use Walter Bislin's calculator, 295 meter building at that distance with standard atmospheric refraction would need an observer height of less than 15 meters above the water for the top of the building to be visible. And according to the elevation finder, there are multiple locations along the lake edge which reach observer heights of 50 meters above sea level. So there are certainly locations across Lake Michigan where the top of Chicago's skyline would be visible on a non-strawmanned version of the globe. But we can't know for sure from this meme because it doesn't give the observer location. It would be handy if they, included the GPS data, although GPS proves the globe as well. Now, I know flat earthers will then make posts like this, claiming there's no such thing as satellites and that GPS is ground positioning, not global positioning, and that it's using balloons or cell towers to get a location fix. When in reality, GPS functions specifically with the globe in mind. But you know what? I'm not going to debunk this one. I'm going to let today's sponsor, Brilliant.org, debunk it for me. Because if I open up the app, you can see there's dozens of courses on various different subjects. We've got maths, we've got computing, we've got data, we've got science, logic, everyday maths, and then one on technology. And one such course on how technology works, which I have actually already completed, but we can go back through the topics. So level 1 is classes about algorithms, and then we get to level 2, and there's a class here called GPS location. Although the one before it, location services, is actually quite relevant to this. And so we're met with this, network-based location. Your phone can estimate its distance from the cell tower based on the strength of the signal. So obviously, the further away from the cell tower, the signal gets weaker, so your phone can use that to roughly estimate how far away it is. Your phone estimates the cell tower is between 3 and 4 kilometers. Adjust the range of possible positions to match this. So we can move these little sliders around, so we need a maximum range of 4 and a minimum of 3. So we now know that the phone is somewhere within that circle. It would be unusual to only be in range of one tower. You can get a better estimate of your position if you know the distance to a second tower. So now it's given us a second tower. Our phone knows the approximate distance to each one of the two towers. So for each tower, the phone could be anywhere within these two circles. But only where the circles cross can the phone be the correct distance from both towers at the same time, which means we can narrow it down to one of these two locations. If we know we're on Earth's surface, an accurate distance measurement of 3 points is enough to know our exact location. And so that's the end of that lesson, and then we can move on to the GPS class. So, GPS location works in a similar way to locations from a cell tower. Satellites send signals which include their exact location at the time the signal was sent. We need to know how far we are from each satellite. The satellites can't broadcast this information, but they can send the broadcast time. If your phone has the broadcast time, the arrival time of the message, and the signal speed, how can it work out the distance to the satellite? Well, much like if you were driving in a car. If you know how fast you're traveling and you know the time difference between you setting off and you arriving, you can multiply your speed by the amount of time you've been driving for to know how far you've traveled. So I'll say we find the time difference and we multiply by the signal speed. That's right. Now that we know how to get the distance to one satellite, let's see how many of these distances we need to pinpoint our own location. GPS satellites are not on Earth's surface, and the location technology does not assume we are either. Where could the phone be if it's at a known distance of r from the satellite? So the GPS satellite is broadcasting in all directions, so your phone could be anywhere, in any direction, r distance away from the satellite, which means it's anywhere on the surface of a sphere around the satellite. So we'll go with the third answer, and that one's correct. So there's a sphere of possible positions marked here with blue dots. Some of them might seem unlikely, like those underground or out in space, but they're all possible in principle. And it gives us this little animation that we can move around to see. So the satellite is in the middle of all of these blue dots, and the blue dots are each a location where a phone would be that right distance away from the satellite. With two satellites, we get points on the surface of both spheres. Where could the phone be once it knows its distance from two satellites? And again, it gives us this little animation that we can play around with to visualize it. And in reality, it could be anywhere on this blue circle where the two spheres overlap. With three satellites, we can pin your location down to 2 points where all three distances intersect. Is this enough to give an accurate GPS location? Well, no, because there's two possible locations. You guessed it, we can add the distance to one more satellite to find a single point where all four intersect. And that is the end of that class. So, if GPS devices like this were using cell towers, they would only need links to 3 data sources to figure out their location. But this won't get a position fix unless it's locked onto 4 locations. But the other problem for Flat Earth comes from the fact of what was mentioned at the beginning of that class. The GPS satellites broadcast a signal which is just the broadcast time. And then the receiver compares the broadcast time in the signal to what the time is when the signal's received, and it multiplies that difference by the speed of light, which is how fast the signal is traveling, to then work out how far the receiver is from each of the sources. Well, the GPS units are working out that they are 20,000 plus kilometers away from the source of the signal. So for Flat Earth, that either means the balloons are going more than 20,000 kilometers away from everywhere on Earth, or the manufacturers of the GPS units are fudging the coding and making out like they're calculating for a globe when they're not, which would be easy enough for flat earthers to go and check. So, Brilliant.org can debunk Flat Earth, and even if you don't want to debunk stuff with it, it's still a great tool for learning in general. As you can see, I'm closing in on 1,000 consecutive days of completing lessons. And if you like the look of it too, you can try it for free today by visiting my link brilliant.org/Brilliant Dave McKeegan, which will also get you 20% off an annual subscription. Now, on the topic of satellites, this is a meme I often see. Internet connected by satellites, a myth. Internet connected by undersea cables, a fact. Except what people seem to overlook with this is, before Starlink, any satellite internet was transmitted through satellites in geostationary orbit, which is a distance of 36,000 kilometers or 22,000 miles. That's almost the circumference of the globe, and every signal has to travel that distance twice. Once from the sender to the satellite, and then from the satellite back to the receiver. And that's assuming that it's a single satellite that can see both locations. If the signal is going to somewhere on the opposite side of the Earth, then it needs to be passed through multiple geostationary satellites. All of this means huge latencies with the signals. Whereas cable internet is much faster, because the signals don't have as far to travel. Plus, a satellite can only handle a certain amount of data at a time. So if everyone on Earth was trying to use geostationary satellites for transmitting data, everyone's speed would be bog slow. Whereas huge cables can handle much higher data throughput. Satellite internet was just a convenient solution for people who are in locations that don't have direct internet access. That is changing somewhat these days with Starlink, which has many more satellites and that are much closer to Earth, so the signal travel time is significantly less than going to geostationary. And Starlink is definitely a thing. I mean, when we were in Antarctica, we were using Starlink. The main camp at Union Glacier has a Starlink setup of its own, but we took our own Starlink antenna for use at Halfway Point, which was set up by laying the antenna flat on the roof, pointing straight up into the sky. No undersea cables or cell towers anywhere in sight, and yet we were able to livestream. Trying to argue undersea cables exist, therefore satellites are fake is ridiculous. It's like trying to argue that cargo planes must be fake because we're still using cargo ships. Next, let's tackle this one. The liftoff requirements for Earth versus Moon. Suggesting the idea of lifting off from the Moon in a lunar module is absurd given the size of the rockets needed to leave Earth. This boils down to 3 basic concepts. How much mass are you moving? What speed does that mass need to reach? And how much resistance will there be? The more mass that you're trying to move, the more force is required to move it. The higher the target speed, then either more force or force for a longer period of time is required, i.e., you can speed up a lot in a short space of time, or you can speed up gradually over a long period of time. And if you're fighting against resistance, you then need more energy to overcome that resistance. For example, if you were walking along a road, easy enough to do, very little energy required. But if you had a huge weight that you were also needing to move, then the amount of energy you need to exert increases. If you need to get that weight to a higher speed, then you're going to have to push much more, which again, more energy required. And if the surface that you're pushing the weight along has a high resistance, like tarmac, it's much harder than if you have a surface with much less resistance, like ice. So, in the context of spaceflight, only the ascent stage of the lunar module actually launched off the moon, which had a weight on Earth of around 10,000 pounds or 4,500 kilos. And crucially, the weight of the payload that was needing to actually get to lunar orbit was about half that. 4,800 pounds or just under 2,200 kilograms dry mass for the ascent stage, plus 2 people and around 100 pounds or 45 kilograms of rock samples. Versus the SLS, which is the rocket shown in this meme, which has a liftoff mass of 7.75 million pounds or 2.6 million kilograms. That gets a payload of 209,000 pounds or 95,000 kilograms into orbit. So SLS is trying to carry more than 43 times the payload into orbit, and the speed it needs to reach orbit varies. Because the moon is smaller than the Earth, the lunar orbit velocity for the ascent stage is around 1,600 meters per second or 3,600 miles per hour, versus the velocity needed to orbit the Earth of about 7,800 meters per second or 17,500 miles per hour. So not only 43 times more payload mass, but it needs to be accelerated to almost 5 times the velocity. That is naturally going to need more energy to achieve. Then we have resistance. If you launch a rocket on Earth, you are fighting against a constant barrage of air particles like somebody trying to cross a crowded room. Whereas if you launch from the moon, there's barely any particles to slow you down. Plus, you have gravity to factor in. Because the Earth is much larger than the moon, then the strength of the gravity is much higher, being 9.8 meters per second squared versus around 1.6 meters per second squared on the moon. And the strength of the gravity fades as you get further away, but again, because the Earth is larger, the rate at which it fades is much slower than the moon. So from the moment anything leaves the surface of either the Earth or the moon, you have gravity acting to bring it back down. So a rocket needs to overcome that constant resistance, but the resistance is much greater when you're trying to leave the Earth. On the topic of the moon, we then have ones like this. Sky from Earth, sky from the moon. Anybody else see a problem here? Yes, the moon is lit and the Earth is lit, and they're not overexposed, meaning the camera is exposing for daytime. The light from the stars is too dim to be picked up by the camera. It's the same reason you don't see any city lights on the shadow side of the Earth either. Apollo 16 actually did take a telescope and set it up on the moon to view the Earth from the lunar surface, and it was able to pick up the stars, but not without turning the Earth into a glowing white orb. Another favourite meme of mine that I see about the moon is this one. On July 21st, 1969, Neil Armstrong was the first man to walk on the moon. That same day, this picture was in the newspaper. A quick reminder, it was a 3-day flight back and those pictures had to be developed in those days. Now, everything stated in that meme is actually correct. July 21st, they walked on the moon. It was a 3-day trip back to Earth. They landed back on July 24th, and the photos that they took during the mission did then need to be developed. Of course, what this meme is doing, without explicitly saying it, is trying to steer people down the mindset of thinking, Well, how could the newspapers publish that photo before they'd even got back to Earth? And the answer's simple. Because this image is not a film photo that was taken on the moon, it's part of the TV broadcast which was transmitted back to Earth live at the time. That broadcast was shown to everyone around the world on July 21st. The newspapers basically had to take a photo of the TV so that they had an image to use in the newspaper, precisely because the better quality photos wouldn't be available for a few weeks after. Many of the photos taken were then shown during the press conference that the astronauts had on the 12th of August. And around that time, you then had the photos being used in publications. I.e., Time magazine released a publication the day after they returned to Earth, but they had to use a painting of Armstrong that was adapted from one of the training photos. Yet, on the 11th of August, Life magazine published a special edition magazine on Apollo 11, using lots of the 70mm photos and even some of the frames from the 16mm camera as well. And finally, let's wrap this video up with what I can only describe as a complete lie. Geodesic measurements were done between the bases and tops of two buildings in Brazil. One in Terres and another in Natal, 1,895 miles apart. If the Earth were a globe, the distance from the bases of the buildings should be shorter than the tops. Unfortunately for Ball Earth believers, the measurement between the bases and tops were identical, meaning curvature is non-existent. Now, firstly, I do find it amusing that they say geodesic measurements were taken, because geodesic, by definition, is measuring along a curved surface. Secondly, something like this can theoretically show the presence of curvature, as in if you had a series of towers back to back covering a long enough distance. If the Earth is curved, then the rope going through the tops of all of the towers would be longer than a rope running through the bottoms of them, whereas on a flat Earth, both ropes could be the same length. But the difference would be very slight. If you had a series of towers running for 16 kilometers or 10 miles, and each tower was 20 meters high, a rope running along the top of each tower would be only 2.5 centimeters longer than a rope running through the base of each tower. The problem with this meme's claim, though, is what they're suggesting would require a direct measurement of the gap between both the base of the two buildings and the tops of the two buildings, which would show a difference in length on a globe if you could actually do it. But at almost 2,000 miles apart, you can't see both buildings at the same time. There's other buildings, entire cities, and hills between the two of them. And looking at the video link that gets mentioned in the meme, it only shows them using a theodolite to measure each building from next to each building. Well, that would give you the height of each building respectively, but not the distance between the two of them. Anyway, that's going to be it for this video, I think. I've got plenty more memes that I could cover, but maybe I'll just save that for another day. As always, feel free to leave your thoughts in the comments down below. If you enjoyed this video and you haven't already done so, then please do consider hitting the like and subscribe buttons, and hopefully we'll see you in the next video.